This will hopefully be quite an exciting video because of its complexity. And so to just simplify the previous questions we've done, we've been asked to prove that RT equals WR times RP over RS. Now, there's two things that help us to get to these ratio fractions. The one is the simple, when you see a triangle with parallel lines, you can do the sides are in proportion. And if I could do the bottom here, RT over the top, PT is equal to the bottom, WR over SW. Or I could do some version of the entire line. So I could say RT over the entire line, RP equals WR over the entire line, SR. So there's a whole bunch of combos you can get out of this. The other way that I can get ratio fractions is by proving triangles similar, which we've done in the previous question. And you do that by finding 2, and then the third angle will be the same. And I, as a habit, like to always write the ratio fractions immediately after doing this. Then you get to the question which we're going to tackle today, which is this monstrous one, which when I see squares, I think it could be Pythagoras. When I see a bit more than just a normal ratio, my brain often thinks that it could be a combo of two sets of ratios, and that's what a lot of this video will hinge on. And so the first question, RT over the entire line should be the same as WR over the entire line. And that's what we were asked to prove before this video began. And so that's what we've done in a previous question. We've got RT, and we did it from the sides in proportion. As I mentioned to you, as a habit, from here, if we prove these similar, I wouldn't even waste a second, and I would do the first 2 over the first 2 equals the second 2 over the second 2 equals the first and last over the first and last. Now we get to our monstrous question of trying to prove this. What I do to do this is I just look where I see those. So I see a WR here, I see a SR, there's one of them, I see a RP, there's another one of them, so we definitely want to use this. I don't see a RT, but that's not the end of the world because it could be substituted in. So don't stress about that. I see a RQ that's here. I see another RS and another RP here and here. And again, the missing RT. So these will be the two of the ratio fractions I'll hinge on, and I'll use the previous question. So watch as it happens. I'm going to substitute this in up here. So it will be WR times RP over SR. And it's all being divided by RQ, which to me starts to get a little bit messy, so I'm just going to put it over 1, and I'll tip in times in the next question. So this is RT over RQ equals to RS over RP. You've got all of that from here, and basically just a substitution. Then to make my life easier, I just want to simplify this for you guys. So this is RQ over 1. I'm going to tip in times and make it 1 over RQ. And what that will do is it will, when I do 1 over RQ, the RQ will be at the bottom. So this is where we've got to, and we're trying to get to this place in highlighted here. So all I need to do is I need to get rid of the RP that's up here. That's going to move down to the bottom. So that will make a RP squared. I want to get rid of the RS. That's going to times up here. That will give us the RS squared. And I'll be left with the WR and the RQ. And there I've proved what I needed to. So look out for these quite complicated questions. It's normally a combination of two different, either similar triangles that you've got all the ratio fractions and you put them together, or like this example, a combination of sides in proportion from the parallel line triangle as well as similar triangles. And it was literally in some ways as easy as just doing a substitution and then just going about it carefully. I hope you enjoyed this juicy question. If you did, please like it. subscribe to our channel and share this with your friends.